Hello friends, myself Professor Rajendra Baburao Garse, working as an head of Electrical Engineering Department at NB Navle Sinhagad College of Engineering, Solapur. I am having a teaching experience of 9 years. In the qualification, I have completed BE Electrical from Government College of Engineering, Karad and MTech from Indian Institute of Science, Bangalore. I have secured the All India 7th rank in the GATE examination with a 99.96 percentile. Also, I have qualified the GATE examination 6 times. In my last video, we have discussed about voltage control techniques. In today's video, we will discuss about the harmonic reduction techniques from output voltage of the inverter, right? So harmonic reduction, right? As we have discussed, we are having the different types of the inverters: single phase half bridge, single phase full bridge, right? In both the inverters, in the output voltage we are having only odd harmonics present, right? Odd harmonics present means the output voltage of the inverter is a non-sinusoidal, right? After that we have discussed about the pulse width modulation technique, right? In the pulse width modulation technique, yes, we are having single pulse modulation, multiple pulse modulation, as well as sinusoidal pulse width modulation, right? In the single pulse width modulation, yes, the output voltage, that is a pulse width delta, right? We are keeping the pulse width delta which is in between 0 and 180 degree, right? But it is a less than 180 degree and greater than the 0 degree, right? Next, so why the harmonic reductions are required, right? Because suppose if the output voltage of the inverter is practical inverters, right, is directly given as an input to the specific electrical load, as the output voltage consists of the harmonics, right? Whether it will affect on the performance of the load? Yes, definitely. So performance of the loading device fed through the inverter is affected by harmonics, right? So harmonics also causes the additional losses. Okay, next, generally the high frequency harmonics means higher order harmonics, right? Because as we know, the order of the harmonics increases, the frequency also increases, right? For the fundamental component, the frequency is omega. For third harmonic it is 3 omega. For fifth harmonic it is 5 omega. Seventh it is 7 omega, and it's so on, right? So for the higher order harmonics, yes, it is very easy to reduce the or to remove the harmonics from the output voltage. We can do it with the help of filters, right? With the help of filters. So but if you check, as the order of the harmonic is more, what about the its contents in the output voltage? It will be lesser, right? Because as we have discussed, the fundamental component is having a share of 90%, right? What about the share of the third harmonic component? Yes, it is a V01 RMS divided by 3, right? What about the fifth harmonic? V05 RMS is equal to V01 RMS divided by 5, right? So as the order increases, its share goes on decreasing, right? So the harmonics with a lesser order, yes, are the most dominant harmonics. Okay, so we need to remove those harmonics, and it is not possible to reduce or to remove the lower order harmonics, that is a 3, 5, etc., right, with the help of the filters, right? If we go on using the filter, then it will become more uneconomical, and the size of the filter also increases. Okay, next, so harmonic reduction techniques. Now harmonic reduction by the pulse width modulation technique we already discussed. By using the specific pulse width in a single pulse width modulation, by using a specific pulse width we can remove the specific harmonic, right? So we have derived it for removing the nth harmonic. Yes, what is the required pulse width? The required pulse width is 360 by n, right? So for the third harmonic it is 120 degree, for fifth harmonic it is 360 by 5, that is a 72 degree, right? Next, harmonic reduction by transformer connection and the harmonic reduction by stepped wave inverter. Okay, now we already discussed about the pulse width modulation, right? Next we will discuss about the transformer connection as well as the stepped wave inverter. Okay, so here ultimately we are interested in removing the harmonics from the load voltage, right? Load voltage. Now, so here we are using two inverters, inverter A and inverter B, right? For both the inverters the input is same, that is a DC supply, right? Same input. Now let it be Vs or ADC you can consider. Okay, next, the primary of the transformer A, we are using two transformers, right? Both the transformers having a turns ratio 1:1. Okay, the primary transformer 1 or the A is connected, right, to the output of the inverter. The primary and the secondary winding is connected in series with the secondary of the second transformer, right? And the inverter B output is connected to the primary of the second transformer, right? Now these two transformers secondary windings are connected in such a way that whatever the induced voltages into these two transformer secondaries, right, these will be, yes, assisting to each other, right? Or this will be adding, right? Next, so can we say that VAB is equal to VA0 plus VB0, VAB is equal to VA0 plus VB0. Okay, now as it is a 1:1 transformer, right? So whatever the waveform we will be getting, means whatever the output of the inverter, the same will appear as a VA0. Whatever the output of the inverter B, the same will appear as a VB0. Okay, and VA0 plus VB0 is nothing but VAB. Okay, now suppose in order to get VA0 form, right, we are turning on and turning off of the switches in the inverter A, like, okay, so suppose inverter A is a full bridge inverter, right? So at this instant we are turning on switches S1 S2, right? At this instant we are turning off switches S1 S2 and we are turning on switches S3 S4, right? Similarly here S3 S4 turned off and S1 S2 turned on. At this instant S1 S2 turned off and S3 S4 turned on, and so on. Okay, now here VB0, right? If you check the waveform of VB0, right, whether it is in phase with VA0, no, right? So what we have done, we are in the inverter B, whatever the switches we are having S1 S2 S3 S4, right? Because A and B both the inverters are the full bridge inverter we have considered, right? So for the inverter B at this instant, right, we are turning on switches S1 S2. This waveform is for continuous cycle, right? For very first cycle what will happen, for very first cycle it will be 0 here, right? It will be 0 here for short period. Next, at this instant we are turning on switches S1 S2. Again at this instant we are turning off switches S1 S2 and turning on S3 S4. Again when S3 S4 are in the on state, in the output will be getting negative voltage, right? So here again S3 S4 turned on, S1 S2 S3 S4 turned off, S1 S2 turned on. Again at this instant S1 S2 turned off and S3 S4 turned on, right? So we have operated the switches in the inverter and inverter B, inverter A and inverter B in such a way that there exists, yes, a phase displacement of angle theta, phase displacement of angle theta between the two inverters, Okay, next, now so as we know the voltage across load is equal to addition of these two voltages, right? So if we add during this interval, yes, what is the output voltage? It is a plus Vs minus Vs, so it will be 0, right? Next, from here to here, right, means during this interval, so Vs plus Vs, it is a 2 Vs, right? So it is a 2 Vs. Next, again minus Vs plus Vs, it will be 0 for this much of interval, right? After this again minus Vs, so it is a minus 2 Vs. Again after this interval it will be 0, again it is 2 Vs, again it is a 0, right? So if you check the output voltage of the output voltage of the circuitry or the voltage across the load, it is a Cauchy square wave, right? And as we know, in the Cauchy square wave definitely it will be consisting of a lesser harmonic compared to that of the square wave, because we have already discussed in the single pulse width modulation the output voltage is, it is a Cauchy square wave, right? Are you getting the point? Okay, we can achieve we can remove the harmonics, right? Next, second is okay, or similarly, yes. So by keeping how much phase displacement, which harmonic can be removed, we are going to discuss in this same method only, right? So here, suppose the phase displacement is theta, right? Phase displacement between the two is theta. So here, can we do the Fourier series analysis of VA0 and VB0? Yes, for VA0, what is the Fourier series analysis? Yes, same as that of the whatever we have discussed in the single phase full bridge inverter. Yes, it is 4VA. Instead of EDC, it is a 4VS, right? So it is 4VS by pi, right? Sine of omega t plus, for the fundamental it will be 4VS by pi into sine of omega t, right? Plus for the third harmonic it is 4VS by 3 pi into sine of 3 omega t, right? So I have taken 4VS by pi common, so it will be 1 by 3, right? For the fifth harmonic it is 4VS by 5 pi, so it is a 1 by 5 into sine of 5 omega t, and so on, right? Similarly, what is the VB0? VB0 is 4VS by pi, as the phase displacement between the two is theta, right? Suppose if we keep the theta is equal to pi by 3, then it will be sine of pi by 3 minus theta. Here it is a 1 by 3 into sine of 3 into omega t minus pi by 3, right? Sine of omega t minus pi by 3, right? Plus 1 by 5 into sine of 5 into omega t minus pi by 3, right? So if we add VA0 and VB0, yes, what will happen? If we multiply with these 3 here, then what will happen? Sine of 3 into omega t minus sine of pi. So if the, what is the phase angle here? Phase angle for the third harmonic component here, sine of 3 omega t, and here phase angle it will be sine of 3 into omega t minus pi by 3. So it is like sine of 3 omega t minus 3 into pi by 3, that is sine of 3 omega t minus pi, right? So if you check, here phase angle is 0 and here phase angle is sine of 3 omega t minus pi, means phase angle is 180 degree. So can we say that the third harmonic component in the VA0 and the third harmonic component in the VB0, yes, these two will be in completely out of phase. These two will be completely in out of phase. So whether these two will get cancel each other, definitely these two will be cancel each other. So for this method, if we keep phase displacement between the VA0 and VB0 is equal to pi by 3, yes, the third harmonic will get cancel out, right? So similarly, for removing the fifth harmonic, what will the required phase displacement? So yes, here we need to keep, instead of pi by 3, we need to keep pi by 5. Yes or no? So it will become 5 into omega t minus pi by phase. So it is sine of 5 omega t minus pi. So here phase angle is 0 degree. Here it phase angle becomes equal to pi, right? So similarly, so from this we can write, if phase displacement between third harmonic component is equal to pi radian, then they cancel each other. If phase displacement between VA0 VB0 is adjusted to pi by 5, then fifth harmonic component can be eliminated. Are you getting the point, right? So this is the one method, okay? So by keeping the particular phase displacement between VA0 and VB0, we can remove the particular harmonic, okay? Next, harmonic reduction by stepped wave inverters. It is very easy. Harmonic reduction by stepped wave inverters, okay? So to inverter A, inverter B, right? Output of the inverter A is given to the primary of the first transformer. Output of the inverter B is given to the primary of the second transformer. Both the inverters are having the same input, okay? Next, the secondaries of the both the inverters are connected in such a way that these two will be adding to each other, okay? Next, here turns ratio is 1:3, here turns ratio is 1:1, okay? Next, yes, here we are getting VA0. VA0 means what? VA0 is nothing but the voltage across the secondary of the first transformer, right? This is a VA0 and this is a VB0, okay? This is 1:3, so be careful, okay? So we are, for the first inverter, okay, we are operating the switches in such a way that at this instant, means from here to here, no switch will be turned on, right? At this instant we are turning on switches S1 S2. So at the will be getting Vs. So at the secondary it will be 3 Vs. At this instant we are turning off switches S1 and S2. Are you getting the point? Okay. Next, for the second inverters, we are operating the switches in such a way that yes, at this instant S1 and S2 are turned on. Here S1 S2 turned off and S3 S4 turned on. Here S3 S4 turned off. So from here to here, none of this switch will be in the on state. Again, yes, S1 S2 on, S1 S2 off, and like this we have developed this waveform. Okay, addition of these two is nothing but your output voltage. Okay, so here 0, here it is Vs, so output voltage is Vs. Yes, 3 Vs, here it is minus Vs, so 3 Vs minus Vs, it is a 2 Vs, right? 3 Vs minus 0, it is a 3 Vs. Vs plus Vs, 4 Vs. After that 3 Vs minus 0, yes, 3 Vs, right? Vs minus 3 Vs minus Vs, 2 Vs, right? And here it is 0 plus Vs, so it is a Vs. So can we say that it is a sinusoidal waveform? This is only first half cycle. Okay, only half cycle of the output. So whether this waveform will be more closer to the sinusoidal compared to the quasi square as well as the square wave? Yes. So definitely this waveform consists of the lesser harmonics, right? So this is the second way or the second approach to remove the harmonics. Okay, thank you, thanks for watching.